Welcome back, guys. We're here looking at review questions again. Number 6.
Let me read it out of your book for you guys. A 15 megahertz AC capacitor is connected in series with a 50 ohm resistor. The capacity has a voltage rating of 600 WVDC. The capacitor and the resistor are connected to a 480 volt 60 hertz circuit, and the voltage rating of the capacitor sufficient for this connection. So, in this, we are given that C is 15 megahertz AC, our R, or our resistance, is 50 ohms, and our rating of the capacitor is 600 WVDC. So we're looking for the voltage given 480 volts in a 60 hertz situation. So is it sufficient?
All right, first thing you got to ask yourself, and I did, is what does WVDC actually mean? And I'll be honest with you, I don't know. However, the only thing I could come up with is it might be the rating for a wet type capacitor versus a dry type.
Obviously, the VDC is voltage in DC.
Well, yes, exactly. So that's why I basically went under the assumption that it is voltage in DC, and somebody threw in a typo there. I could be wrong, and I'm not going to throw something like that into an exam for you. So with that in mind, I'm looking down here as I've got a 480 volt system that is an RMS value. If we look at what the peak value of that circuit is, RMS, remember RMS is looking at the DC equivalent of an AC circuit. All right, so in this case, the peak value is square root of 2 times the RMS value, okay? And when we plug those numbers in, you've got 480 volt times 1.414 is equal to 679 volts DC. That definitely exceeds a 600 volt DC rating. So keep in mind that you're pounding that 60 times every second. You're hitting that dielectric with that voltage that it's not rated to take. So I would definitely not use that for your system. All right, so no, need a higher rating. All right, number 7.
Number 7 in the book says, an RC series circuit is connected to a 120 volt 6 hertz power source. The resistor is 25 ohms and has a voltage drop of 65 volts. What is the capacitance of the capacitor?
So in this case, what we've got here is we have RC, so resistive capacitive circuit, in series. The voltage that we've got is 120 volts, and it's at 60 hertz. The resistance is given a value of 50 ohms, and the voltage on that resistor is 65 volts drop.
Does it say 50 ohms or 25 there?
Excuse me?
50 or 25 there? The resistance, yeah.
Okay, so now what they're asking us to do is find the capacitance. And here they're just torturing us again. All right, so in order to be able to find the capacitance, obviously I need to find the circuit reactance associated with the capacitor. All right, so in order to find that reactance, looking at what they've given me so far, I'd like to find a current, and I'd like to find the X sub C. Well, the X sub C, okay, I'm sorry, the V sub C, I'm sorry, the voltage drop across, because we have a total voltage and we have a resistive voltage. That's the voltage dropped across the resistor. So if we go to the book in the back, it says that the voltage associated with the capacitor is, again, square root of sum of squares. Okay, the total being the hypotenuse of the right triangle squared minus
The other way.
the resistive voltage squared, and then taking the square root to give us our associated drop across the capacitor. Now, we plug those numbers in, we get 120 squared minus 65 squared, and again, keep in mind square root, all right, which comes up to be 14,400 minus 4,225. Okay, and when we do that and take the square root of it, it comes out to be just slightly more than 100 volts. All right, which again, what's that tell you? A lot of your voltage is being dropped across the capacitor in this case. Now that we've got the voltage, we need to find the current. All right? Knowing that we've got a series circuit and knowing that all the currents are the same, we can go up now and calculate what the circuit current is using Ohm's law. And the simplest way to do that is we're given two values here that both refer to resistors, and that is the voltage and the actual resistance. So we can calculate the current, therefore, is going to be the voltage associated with the resistor divided by the resistance, which is 65 divided by 25, which ends up being 2.6. But that's also equal to the total current and the reactive current, the capacitive current, I should say. But they're all equal, so we now have enough information to be able to find X sub C. So X sub C now is going to be equal to the voltage drop across the capacitor divided by the current that the capacitor is going to see. So we have those values, we plug them in, and we get 100.1 divided by 2.6, which comes out to be 38.5. Now that we have the reactance, we can go back and use our basic formula that says that the capacitance is equal to 2 pi frequency being 60 hertz, okay, this is the reciprocal of this value, okay, times the reactance. So we have, plug in the numbers in, we have 1 divided by 2 pi f, 60 hertz, comes out to be 377, times 38.5, which we just calculated up here. And once we do our calc, we come down and it's looking at us having a reciprocal of 14,500. When you plug that number, do a 1 over x in the computer, you're going to get
a small decimal number.
a very small decimal, okay? Now, to convert that number into something that we're used to seeing, we want to shift it. We could go 6 because we know that we use microfarads quite a bit. All right, so we shift it 1, 2, 3, 4, 5, 6, and we're left with the decimal point being between the 8 and the 9, so it comes out to be 68.9 microfarads. And that is it. I've got one more problem I've got to work out. I just ran out of board space, so I'll be back.